problem set is due on Monday.
Wait,
Here, due on Monday.
this Monday.
1 page.
My closet.
Are you sure?
2 pages. Wait, can I have a problem set, please?
No.
Oh, can I have a couple
You can have it.
Guys, settle down. I can't hear people asking me questions. Okay, I'm about to print off 1 problem set. Okay, Michael, did you have a question?
Yeah, can I move up a couple seats?
Absolutely.
No. No.
Okay, what other bums are we missing?
Leah.
Wait, let's vote.
What?
Can I sit over there?
Are you sure?
Just for today.
Okay.
What?
Don't make me regret it.
He said he's gonna sit there.
Really?
Yeah.
Someone's NHS down.
It's mine.
Oh,
Okay. So yesterday we talked quite a bit about the different types of intermolecular forces. A couple of key points. Did we talk about 2b2?
No.
maybe. What's 2v2?
We were on 2v1.
No.
I wrote it down.
Okay, so we talked quite a bit about the London dispersion force. 2b2 is about the dipole-dipole interaction. Actually, it's about lots of interactions, because they talk about ionic interactions with dipoles. No.
Oh. Oh, is that the thing that occurs like when stuff dissolves in like water and there's like ions?
What was the question?
So if you read through this, there's a whole bunch of different interactions that it talks about. It starts by talking about the dipole-dipole interaction. The dipole-dipole interaction, I have a nice little picture that shows it on the notes. Every one of those molecules is a dipole. It has a positive end and a negative end. And you can see with the green arrows the attractions between oppositely charged ends and the repulsions between the similarly charged ends. Okay? But when the attractions are greater than the repulsions, we get an overall pull that keeps the molecules together. Okay? In this case, we're talking about the dipole-dipole interaction. Permanently polar molecules attracting each other, positive end of one to negative end of another. An exceptionally strong version of that is called hydrogen bonding. Saw it in the simulation that we played around with, right? The key things to understand with hydrogen bonding is that what we really need to have hydrogen bonding is an OH, an NH, or an FH bond. Once we meet that requirement, that bond, the hydrogen in that bond will then form a hydrogen bond, will form an exceptionally strong intermolecular interaction with another atom of nitrogen, oxygen, or fluorine. Okay, so in this DNA, that's what we looked at in the simulation, here's your NH bond. That H does not have to interact with another NH. It's interacting with this nitrogen that is connected to 2 carbons. Okay, but if we have that NH, we have satisfied the requirement for having the possibility of having hydrogen bonding.
It doesn't work if there's another H though.
Another H where?
Right there.
If this thing had an H off of it, no, because then
Yeah,
they
because that
both
would be
be
repellent,
positives. Yeah. Okay. But if the H was coming off this way, it would be possible for this thing to form a hydrogen bond. Okay. But the point is that the hydrogen bond, this thing does not have to form its hydrogen bond with another NH. We could have an oxygen that's double bonded to a carbon. And as long as we have this nitrogen that's pulling the electrons away from that hydrogen very strongly, this hydrogen will form a very strong interaction with any other highly electronegative element. And this is your hydrogen bond.
Wait, for the other atom, you said nitrogen, oxygen.
this other atom that the hydrogen is forming the bond with, the H bond with, this has to be a nitrogen, an oxygen, or a fluorine as well. So it's almost like that hydrogen is being sandwiched in between two highly electronegative elements. And the reason we think that there is something called hydrogen bonding is because of this graph. This graph shows us a whole bunch of stuff from 2b1 and 2b2. If you look at the dark blue points on here,
Is that red one? Is that red one hydrochloric acid? Oh, because of the spacing.
it's what?
Because of the spacing. The second red one.
HCl, yeah.
Okay.
Yeah, it's not H.
It most certainly is not.
It's A.
Okay, so the ones in the dark blue are actually all nonpolar because they're all tetrahedral. And so the dark blue on the very bottom.
Yeah, that's purple. That's purple, my man.
The bottom one?
What are you comparing?
Okay,
it to?
that's like that's not purple chocolate. That's like the.
Yeah, exactly. Yeah, exactly.
All right, it's purple. The purple one on the bottom is representing all nonpolar molecules. Why is the boiling point increasing?
Electricity, so it has like partial.
Okay, one of the common misconceptions
Okay.
is that students try to explain differences in the intermolecular forces by differences in electronegativity. They try to say, oh, one is more electronegative than the other, so it well, something. No.
Doesn't affect that.
Electronegativity allows us to figure out whether a molecule is polar or nonpolar. After that, we're done with electronegativity. Okay? To explain these differences, we have to understand the London dispersion force. And that the London dispersion force, I almost said disperse. The London dispersion force increases as the size of the molecule increases. That's why that purple line is increasing. Because SNH4 is bigger than CH4, so it is more polarizable. The more polarizable, the stronger the London dispersion force. And now I can sort of try to make that point even more clear because look at the red ones. HCl, HBr, and HI. Why does HI have a higher boiling point than HCl? It's the biggest. So, more surface area. So, stronger London dispersion forces. Wait a minute. Those are all polar. Shouldn't they have dipole-dipole forces? They do, but those dipole-dipole interactions act in addition to the London dispersion force. So the reason that the red line is above the purple line is because the red molecules also have a dipole-dipole attraction. But the reason that the red line increases up this way is because the bigger the polar molecule, the stronger the London dispersion forces. So big polar molecules still attract more strongly than small polar molecules. Okay? Hold on. Now, if you try to use an electronegativity argument to explain why HI is higher in its boiling point, you're going to have problems because, especially if you can't see the entire table, H and I actually have the most similar electronegativities. So that would be the least polar of those bonds. HCl has the biggest difference in electronegativity. That's the most polar bond, and yet it is the weakest intermolecular force of that group, HCl, HBr, or HI. So it truly is the size of the molecule that makes the bigger difference than anything about the difference.
Okay.
You know.
Please didn't try. Okay, that makes more
If
sense.
I did, I wholeheartedly apologize.
No, yeah.
Yes. Okay? So again, once you use electronegativity to try to figure out whether the molecule is polar, stop thinking about electronegativity. Then think about the size. Big size, regardless of whether it's polar or not, makes it stronger than small. Big polar molecules have higher intermolecular forces than small polar molecules. Now, these three chumps on the left, what's up with them?
Ooh,
They are small, and yet they have very, very strong intermolecular forces
small but mighty.
because of hydrogen bonding.
Oh,
Right? Hydrogen bonding is basically just our sort of hand waving to explain why some things have much, much larger intermolecular forces than expected. Something else special is going on when highly electronegative elements bond to hydrogen, specifically oxygen, fluorine, and nitrogen. Chlorine is pretty electronegative too. So there is a little bit of a higher than expected boiling point for HCl here. We should expect it down here, okay? But it's not a big enough difference that we normally consider HCl to be hydrogen bonded, okay? So I also put on this big idea notes, a bunch of fantastic pictures of hydrogen bonding, in addition to the two that we looked at before. That was water and a couple of DNA bases. I also put hydrogen bonding in ethanol. So ethanol has an OH bond in it right here. Anytime you have that OH bond, you have the possibility of hydrogen bonding. The OH, this hydrogen is making a hydrogen bond with the oxygen of another ethanol.
Alcohol.
That oxygen is also forming a hydrogen bond with the hydrogen back here that's attached to this oxygen. They're actually behind. It's not this hydrogen that's making the hydrogen bond, it's the one you can't really see behind the molecule. All right? So we specifically talk in the outline about different cases where you have to maybe look at representations of hydrogen bonding. I also put a couple of specific examples from the biology world.
Uh-oh. mRNA?
No. Protein structures. The two major components that you'll see in a protein structure
Are the protein?
are what, Michael?
Polypeptides. That's what you'll see, right?
Polypeptides are protein.
Yeah, I know.
Yeah. What are the two main features that we're looking at in protein structures? No. What's that curly green thing?
The helix.
The
Wait, what do you mean? No,
So
it's-
here
it's
is an
just
example.
one. It is a double.
Here's an example of what.
Break time!
This is how a biologist might represent a protein.
You gotta be more organized than that.
It is gross, but it's less gross than.
Don't do it.
It is confusing, but it is less confusing than if you were to actually see
All the atoms?
all the atoms that make this thing up.
Bet. Let's see it.
I don't know if I can even find a good picture.
Be fair.
What's those weird, like,
There's
skulls?
the back is still the back is standing up.
Cranberry looking.
Yeah, they're showing a few of the molecules here. I don't know what protein this is, but maybe this is either like one particular molecule that is actually doing the bulk of the work in this protein. So remember when we did the simulation, you had that. There's the one page where it talked about enzymes and how you have to have a certain shape that interacts with a certain molecule, right? So the protein itself has a certain shape, and this might be representing the particular molecule that fits right into that shape. And then maybe it breaks that molecule apart or does something to it right? Some sort of reaction to that thing. But the features I'm trying to talk about are these little arrows here is one feature, and the little squigglies right there are the other feature. Those are supposed to represent what are called alpha helixes or beta sheets. So the arrows that were sort of flat and going back and forth were beta sheets on the right. Alpha helixes are the little spirally things. Yeah. But what's holding this alpha helix in that twisted shape is hydrogen bonds. The backbone of the protein,
Like, could you squish it like a spring?
maybe very slightly. Okay. But the backbone of this protein is this carbon-nitrogen chain here. And because it's an amino acid, this nitrogen will have a hydrogen on it, so now we have the possibility of hydrogen bonding. That NH, the hydrogen, then interacts with an oxygen further down the chain. There's another NH here that's interacting with an oxygen further down the chain. Here's an NH interacting with an oxygen further on the chain. So that sort of keeps this protein coiled up in this structure we call an alpha helix. The other possibility is that two long chains of the amino acid can interact, and that NH bond here can form a hydrogen bond with the oxygen at a whole different part of the chain. Not just a few amino acids down, but maybe dozens of amino acids down. If this thing then curls and winds its way back, and then curls and winds its way back, we can have relatively long sections of that amino acid that form lots of hydrogen bonds with another long section of the amino acid somewhere further down. Okay, that's called a beta sheet. But the way they're shown is typically that kind of dashed line. That's showing the hydrogen bond. That's just a normal way of showing it. Okay? I also think I showed you this image. Yeah?
The one in the bottom.
Yeah, this
Okay. So this thing kind of combines all the intramolecular forces, the ionic bonding, the metallic bonding, and the covalent bonding that we talked about in 2C. And then on the bottom, it shows the intermolecular. There's a question, somebody had a question about the problem set, whoops, because because it said interparticle. Technically, these are all interparticle interactions. Intra and inter are all interparticle. Intra are just between atoms, inter are between molecules. Did we talk about all these?
Kind of.
yeah.
We talked about the ion-induced one.
We talked about how an ion can induce a dipole in a nonpolar molecule. Basically, anything can induce a dipole in a nonpolar molecule. Even another nonpolar molecule. If that nonpolar molecule just happens to have a uneven distribution because of random motions of its electrons, as soon as it gets that temporary little unevenness in its electron cloud, it can induce a dipole in another nonpolar molecule.
Induced dipole, induced dipole.
Induced dipole is another term for the London dispersion force. Okay. Although a permanently polar molecule can also induce a dipole. So oil and water can form interactions with each other. Water molecules can induce dipoles in oil molecules, which is why they're able to mix. They're not instantly shooting up oil on top and water down on the bottom, because you can form interactions between water and oil molecules. Now, those interactions are weaker than the hydrogen bonds that water forms with itself. So eventually, as the random motions brings water molecules next to each other, they're going to interact more strongly and push the oil out of the way. So eventually all the waters clump together, hands off. Models.
But it's a big one.
No.
If all those ones are old.
Does that mean that density is like just like intermolecular interactions? That's what it comes from, and like size and
density is partially related to how strong the intermolecular attractions are, but also on the size of the atoms and what their mass is and how physically they can fit together, right? Density actually has nothing to do with why these two things don't mix. That's a big misconception.
Yeah, because we did like all those things in like middle school. Where they're
Yeah,
like, look
in
at
middle
all
school
these
they're like,
fluids.
oh, you got all these liquids, why are they separating out? Different densities! Yeah, wrong!
So weird.
Yeah, that's
Wrong!
Gravity influences everything.
They lied to
They
you.
want to.
They lied to you. No. The
It's because
reason
they're all
that,
racist.
the reason that any molecules fail to mix together is because they have differences in their intermolecular forces.
Just accept the differences, overcome
This
them.
is our whole middle school.
I know. We need to become.
It
an
actually
integrated
talks
society.
about this in the outline.
I blame Miss Bell.
I wonder if I highlighted it.
Miss Tipton for the win.
I hate it.
No,
Oh, it's actually
all in this version.
in
Oh,
2B.
the story was cool.
Guys, nobody cares about your horrible middle school
Nah,
experience.
she was cool.
What the?
All the lies they told you in science.
We just have
No.
some, sorry.
Yeah, I'm saying that the story was cool.
Substances with similar intermolecular interactions tend to be miscible or soluble in one another.
Mixable.
So if I take ethanol, that is a polar molecule, and I mix it with water that is a polar molecule, they will be soluble in each other. They will completely mix and not separate out. But if I take propane, or butane, or gasoline, a nonpolar molecule, and try to mix it with water, they will not mix, because the water is going to form stronger interactions with itself than it would form with any of those nonpolar molecules. It can form those interactions. They're called dipole-induced dipole interactions. But the energy of those, even at the high end, is weaker than the low end of the hydrogen bonding interactions. So water would way rather interact with itself than it would with oil. So Osama's sort of bad explanation
It's true.
is sort of true.
Yeah.
Water molecules
A racist.
are racist.
They prefer a
They're
segregated liquid.
intermolecularist.
They prefer a segregated liquid.
They prefer other polar liquids to nonpolar liquids because they can form stronger interactions, right? Water would rather interact with any polar molecule, even if it doesn't have hydrogen bonding, it would rather interact with a polar molecule because it can form dipole-dipole interactions than with a nonpolar where it can only form weaker dipole-induced dipole. Now, ion dipole, we're going to talk a lot about in 2A when we talk about solutions.
Yes, sir.
Because the way that water dissolves salts is to create those forces.
Whoa, what's the thing? Hydraulic press. Oh, wait, no, that's what. No, that's over.
Okay, now, when you go on YouTube and type in how salt dissolves in water, you find some terrible videos. This is well, not the worst I've seen, but this is misleading. Watch what the water molecules do. First of all, the water molecules are just going like this for some reason.
But it's ice.
They are jiggling, that's good. They're supposed to jiggle, right? They are showing the polarity of the water molecule. This is a dipole.
Why is it Spanish? Wait, no, that's not Spanish. That's French.
French.
Oh, yeah, I know. I just
From a
thought-
Canadian university. Relax.
Boy, that's smart.
Okay, now, the problem all these videos have is they are made by animators, and the animators give the water molecules intention. Let's go get him. Let's gang up and get that ion. They all just sort of go in and grab the ion and pull it off. Now, what they're really trying to show is how certain ends of the polar water will interact with certain ions. However, a better simulation of this is this one.
Really?
What the?
Yeah.
It's so
Random
crazy.
interactions.
The water molecules do not have any desire to gang up on that yellow ion. However, this video is based on a simulation. It's not animated, it's actually, they plugged in the rules, Coulomb's law, and what happens is the water molecules, eventually, if enough of them surround that ion and orient there, let's see, that ion must be a negative ion because I can see the hydrogen ends of the water attracting to it.
Sorry.
Michael, did you ever try it?
The seagull has escaped.
We can tell that the yellow is the CL for two reasons.
It's huge.
One, it's bigger. Two, look at what end of the water is pointing towards it, Bobby. The hydrogen end. And the hydrogen end of a water molecule is the positive end. Why?
Because life.
Because oxygen.
Because oxygen's the negative end.
Because oxygen is more electronegative, so it's going to pull the electrons more to this side. This is the negative side, this is the positive side. But only if a bunch of water molecules surround each ion will the sum of their ion dipole forces.
Well, but it goes way faster than what we saw.
Oh yeah. If there was a scale on the bottom, it was in femtoliters.
Yeah, I was about to say femto, yeah.
So the ion forces, their energy goes from 400 to 4,000 kilojoules per mole. The ion dipole force is between 40 and 600. So it's very unlikely that one water molecule is going to form a strong enough interaction with any ion to pull it off all by itself. You have to have multiple water molecules forming multiple ion dipole interactions before those attractions are stronger than the ion-ion attraction holding the ion in the crystal lattice. Okay, we'll talk more about that in 2A. What we do need to talk about, so you guys can do the homework, forgot, I got a bunch of fantastic pictures of all those different intermolecular forces. So you can take a look at those. I want to talk a little bit about 2B3. It mentions some properties that are related to the intermolecular force. We already mentioned boiling point.
Yes.
Why is boiling point related to the strength of the intermolecular force?
Because the bigger it is, the more force it goes. Or like the electron or whatever.
The stronger the forces between the molecules,
The more polarized.
the larger kinetic energy they have to have in order to overcome those forces. Temperature is a measure of kinetic energy. It's a measure of the speed of the particles, right? You can actually represent all of these intermolecular forces
It's physics.
with one of these.
Oh.
This graph we use to explain the covalent bond, but it can also explain the intermolecular attraction, right? There's some distance where that intermolecular attraction minimizes the potential energy.
Well, in orientation, right?
And probably a certain orientation as well, right? And if those molecules get too close together, they're still going to repel each other. It's going to be the best YouTube video ever. 6,000 Myrakovs.
At least
What?
At least I'm a call.
No, you're just talking, so it's...
Just our family in general.
Now, if these particles are attracting each other, it's almost like they're trapped in this little well, right? But if I give them enough kinetic energy, they can escape from this well and separate from each other. That's what they do when they boil. I have to give them enough kinetic energy that they're moving fast enough to escape those intermolecular interactions, right? That's it. Let's heat this bad boy up. Now, is it boiling?
No, a little bit.
couple
Wait,
of them.
some of them are
What do we call something that's boiling a little bit?
simmer.
No.
I don't know.
Sizzle.
Just
Boiling.
flying away.
Bubble.
Evaporation.
Oh.
Sorry that the mousy evaporation that was at a 10 decibel level. Sorry. Boiling point is a very specific definition. Boiling point is the temperature at which the vapor pressure of a liquid equals atmospheric pressure.
Yes, sir.
So in this simulation, there's no atmosphere above the liquid. If it was a true simulation, there would be air molecules bouncing around on top of that liquid, and the air molecules could bounce in and keep that liquid in the liquid state. Now it is possible, even with air molecules bouncing around here, it is still possible for one to escape into the air and then get carried away, and it's evaporating, right? In any sample of liquid, some of the particles are moving slow and some of the particles are moving fast. And if those fast ones are right at the surface of that liquid, it's possible for them to escape, overcome their intermolecular forces, and go into the gas phase. What's special about the boiling point is that normally that liquid, even if it's evaporating, the surface of that liquid is held in place by atmospheric pressure. But at the boiling point, we start to get bubbles being produced, right? In order for a bubble to be produced in a liquid, there's got to be air. There's got to be what? If I boil water, am I making air bubbles?
Maybe.
No, I'm making steam bubbles. Right? If I'm going to make a bubble here, then by necessity, the surface of this liquid has to increase by the volume of that bubble, right? Roughly. Okay. So the boiling point is the specific temperature at which the pressure of those particles bouncing around here, here's atmospheric pressure. The air molecules are constantly colliding with the surface here. That's the atmospheric pressure. All these particles bouncing and hitting each other are creating a pressure on the bottom. That's called the vapor pressure. If the vapor pressure is less than atmospheric pressure, we're not boiling. We can be at 99 degrees Celsius and water doesn't boil. It will evaporate very quickly, but it does not boil. It does not have enough vapor pressure to actually push on the surface of the liquid, creating a little bubble down here. It doesn't have that ability until its temperature gets to 100 degrees Celsius for water. Question?
What, does surface tension play any role?
Sure.
Like, depending on the liquid stuff?
Probably.
Oh, and another thing is like, think about the kinetic energy in the molecules and stuff. So if you're like moving the thing while you're heating it up, does that make it heat up faster?
Well, if you mix something, it heats up faster because the rate of heat transfer from the thing you're using to heat it to the liquid is faster.
But like, how about, does the actual moving itself?
No, because the particles themselves are moving at hundreds of miles an hour. You moving it this fast is not going to make those particles move any faster. It's a valid question. I'm just saying.
So
If you think about the actual.
So it has a minuscule effect.
Yeah, it's more because of the convection than it is to any motion. Okay, now I mentioned vapor pressure, and vapor pressure is actually on our list. So I've got this diagram here that shows us how we measure vapor pressure. What we do to measure vapor pressure is we take some liquid and we put it in a container all by itself. So this container is a vacuum and we squirt some liquid in. Connected to that is a tube called a manometer. A manometer is a curved tube with mercury in it. If the pressure on the two sides of that tube are equal, the mercury will be at exactly the same level.
Physics.
If the pressure on one side is greater than the pressure on the other side, the mercury will be pushed up a certain amount. Right?
But if you wanted more precise measurements, couldn't you use something like less, something besides mercury? Or, because like...
Mercury's movement is going to be very small because it is very dense, right? So you have to push really hard on one surface of Mercury to get it to move downwards compared to the other, right? Gravity is pulling down on both of these, all right? And right now we have a vacuum, so there's no particles in here pushing on either surface, so gravity just puts them at exactly the same level. If I break this and I break this and open it up to the atmosphere comes in here and pushes equally on both sides, it's still going to be level, right? But what we do is we keep the vacuum in one end, we spray the liquid in here, and as the liquid evaporates, then we have gas particles in here. Those gas particles bounce around, and they'll hit the surface of the mercury here, creating more force on the mercury here than there is here. The gravity is equal, but the extra gas pressure here pushes this end down. And by the difference in height, we can measure the vapor pressure. Whatever this difference in pressure is the vapor pressure in millimeters of mercury.
Oh, MMHG.
MMHG.
The same thing
Now you could get a bigger change if you used a less dense liquid. However, mercury is a really good liquid to use, person who I'm answering the previous question. Mercury is a very good liquid to use because it doesn't evaporate itself. If you use water in this tube, you'd see a big difference. But water can evaporate, and that puts gas in the tube, which is going to mess with your...
But like, so if there is something like less dense that you could use, would you use it for more precise measurements?
Yes, but it would have to be equally low volatility, which I don't know that you're going to find. Okay. Pressure is a measure of what? Well, it's actually force per area, right? If I push somebody with my hand, and I push them the same force with my finger, I apply more pressure with the finger because there's less area, okay? So we're not really worried about the area because this tube is a constant size, right? But what is the force? Well, for gases, it's the collision of those particles with whatever thing is doing the measuring.
Well, that's
So the pressure that we're measuring with this manometer is really the force of those gas particles colliding with its surface.
impulse.
And so if I put in a liquid, and let's say the liquid has really strong intermolecular forces, very few of those particles are going to get into the gas phase, right? That means you're going to have very few collisions with this surface, and you're only going to move the liquid a little bit, low vapor pressure. But if I put in a liquid with really weak intermolecular forces, let's say I put nitrogen in there, liquid nitrogen. Liquid nitrogen is going to be turning into gas very easily. So you're going to have lots of gas molecules bouncing around in this container. You're going to have lots of collisions here. You're going to have a much bigger pressure, vapor pressure. Does that make sense?
What if you use isotope vapor?
Yeah.
Okay. It's the pressure of the vapor, the gas, that's coming off of that liquid. And we're saying that there's a special term. Actually, vapor pressure follows a curve like this. The higher you heat something, the more vapor pressure, because the more we heat it, the more particles turn into a gas, right? So the more pressure there's going to be. The strength of the intermolecular force is not changing. What I'm changing is the kinetic energy of the molecule. Okay? At a certain point, if we're in air, at a certain point, that force, that vapor pressure, is great enough to actually push against the surface of the liquid. And so down here, these particles are all, moving. They're able to expand and make a bubble. In order to do that, they have to push up the surface of the liquid a little bit. And that only happens when the vapor pressure of that liquid is equal to atmospheric pressure. So these curves represent the vapor pressure at all kinds of different temperatures. Whenever this line hits atmospheric pressure, 760 millimeters of mercury, that's when the liquid would boil. So pentane boils at 36 Celsius. It evaporates pretty quickly at room temperature. At room temperature, its vapor pressure is over half atmospheric pressure. So if I pour out pentane, it's going to be evaporating and it's going to dry up really quickly, even though I'm not boiling it. But if I have that beaker of pentane and I heat it up to 36 Celsius, you'll actually start to see bubbles.
So what does boil
Now,
water do?
I can actually boil a liquid. I can boil water at less than 100 Celsius.
Yeah.
I can boil water at room temperature
The pressure.
if I remove the air pressure above it. Right? The boiling point, this is happening, water's not on here, right? But let's say this one represents water. It boils at 100 under normal atmospheric conditions. But if I remove the pressure above there, then the liquid doesn't have to be moving as fast to create a bubble. So I can actually boil water at room temperature just by removing the atmosphere around it.
Yeah, the triple.
If I make these arrows lower, less atmospheric pressure pushing down, then it's possible for that liquid to form bubbles even at room temperature. I'll do that for you next week.
Surface tension isn't just tension between the air pressure and the vapor pressure.
No, surface tension is really a measure of how strongly the liquids just at the particles just at the surface of the liquid are attracted to each other. Because have you ever heard like there's some bugs that can walk on water?
Yeah.
Or like if you put a paper clip into water, sometimes you can get it to stay there without sinking. Because in order to get into this surface, I have to overcome the intermolecular forces in the molecules at the surface of the liquid.
Okay, so it's how strong IMF is at the surface of
At the surface, yeah. So the stronger the IMFs there are, the harder it is to break through that first layer of atoms. There's also some effects, typically you'll see like beating up of water. If you put a sample of some liquid onto a flat surface, the higher its intermolecular forces, the more it sort of holds itself together.
It's just the right one.
Because of all the forces of these particles at the surface of the bead, high intermolecular force can actually get that thing to form like a ball. If you do it with mercury with really strong metallic bonds, it'll form a nice bead. But if you do it with something like pentane, it'll just kind of spread out because it doesn't have forces between the particles strong enough to hold it together in that bead.
Oh yeah, isn't that what mercury does? Usually like cord?
Yeah. It forms little beads. All right, so a lot of these pictures, a lot of these links are going to help you if you get stuck in any parts of the problem set. But give it a try over the weekend. We're going to talk about it on Monday.
Are we gonna learn chemistry
If you have questions after you read that, yeah.
It's the ball. It's the ball.
The ball. But I'll be darned. Yes, because
We can probably stop it.
Latest?
No worries, we're gonna get more picture of Michael. Michael,
Yeah, because I
smile.
wanna like.
but if
I
gravity
wanna-
Give us a nice
I'm
smile,
really
Michael.
happy we got this.
You're in full view of the camera.
is big,
Yes, we did. Yes, we did. Don't give me the garbage.